So the learning objectives at the end of this lesson, the students should be able to know what is a magnetizing force, to know what is a magnetomotive force, and to know how to calculate the force on the conductor, and to know what is a torque. So these are basically what our lesson overview and the lesson objectives for today. Okay, so on our first slide over here, we have what magnetomotive force. Magnetomotive force. A magnetic field is set up when current flows in a solenoid. And the driving force that produces magnetic flux around the coil is called the magnetomotive force. For example, let's say in electricity, we said the driving force that drives the current through the conductor, we say is called electromotive force. So electromotive force and magnetomotive force, they are they are similar. Okay, this one is the driving force that drives the magnetic flux. But if you come to electromotive force is the driving force that drives the current. So they are all driving force. Okay, so a magnetic field is set up when current flows in a solenoid. The driving force that produces the magnetic flux around the coil, the driving force that produces the magnetic flux around the coil is called the magnetomotive force. It's represented by MMF. So mathematically, magnetomotive force is the product of the number of turns on a wire and the amount of current flowing through the wire. So let's say you take a solenoid. What happens is that if you want to get a formula for the magnetomotive force, is the number of turns on of wire on let's say you are using a nail. The number of turns on that nail times the current flowing through the wire. So the number of turns times the current gives you the magnetomotive force. And each SI unit is ampere turn, or in some books you see ampere. The ampere turn is there because it's the number of turns times the current, and current is measured in ampere. So you attach the turn to it, which is the ampere turn. Okay. So basically, the unit is the formula is MMF equals N times I, where the N over there is the number of turns, and the I over there is the current flowing through the wire. So let's continue. So that's it for the magnetomotive force. We'll be looking at some calculation under this. But let's go to the magnetizing force also. So magnetizing force of a solenoid or a coil is the ratio of the magnetomotive force to the length of the wire. To the length of the wire. So if you divide that means if you divide magnetomotive force by the length of the wire, that means you are going to get the magnetizing force. So basically, magnetizing force is represented by the unit H. It's represented by H. So anytime you see H, is representing magnetizing force. So H equals Ni over L. We said Ni in our previous slide, the previous page over here. Our Ni is our MMF. Now we have the same Ni over here, which is the MMF over L. So the Ni over here represents magnetomotive force. So magnetomotive force divided by the length of the coil represent your magnetizing force, which is H. So where our N over there is the number of turns, the L represents the length of the coil, and the I represents the current flowing through the coil. So N is the number of turns, L the length of the coil, then I is the current flowing through the coil. Now, the SI unit for this is it can be ampere 10 per hot meter, or it's hot ampere per hot meter. Why ampere per meter? We said that magnetomotive force is measured in hot ampere because it's hot. The current times the number of 10. So current is measured in ampere, so ampere. Now we have what? The formula is what? Ni over hot L. Ni represents what? The magnetomotive force. And magnetomotive force is having the unit to be hot ampere. And it's over hot, a unit hot length. And length is measured in hot meters. So ampere per hot meters. So the SI unit is what? Ampere per meter. So anytime you see ampere per meter, it represents what? The magnetizing force of what? A given hot solenoid or a given coil. So let's look at these examples. You can, if you have any idea about it, you can start solving. So the question 1 over there, hot is hot. The magnetomotive force produced when 3 ampere of current flows through 5/10 of a coil. Hot is the magnetomotive force produced when 3 ampere of current flows through 5/10 of a coil. This one we have to find hot magnetomotive force. So let's go back and see the formula for hot magnetomotive force. Then we write down our data and hot solve. Now the formula for hot magnetomotive force is what? The number of turns times what? The current. The number of turns times the current. Let's see whether we have hot these parameters hot in the equation given to us, whether they've given us the number of turns and hot the current, so that we just hot multiply. So now let's go back to the question. Hot is hot the magnetomotive force produced when hot 3 ampere of current flows through hot 5/10 of hot a coil. So the number of 10 over there is hot 5. The current over there is hot 3. So therefore, what's going to be our magnetomotive force? Omo Niger, tell us. Yeah,
Say
Nicholas.
I'm coming. My network was breaking.
Oh, okay, you can mute yourself now. I didn't call you. Amadi Prosperity.
I'm
Amad,
the person. My network was. Say I'm the person. My network was breaking.
so all of your network is foreign you. Okay.
I'm I'm solving it now. Don't worry.
A hand is being raised. Let me see. Yeah, Sedinam.
So these 15 ampere things.
15 ampere 10. You just multiply the current by what? The number of 10. 15 ampere 10. Thank you very much. Nico. Okay. Now let's continue. Now this one. A coil having hot. Yes, Sedinam.
Say mistake, sorry.
Okay, okay. Now, the second question, a coil having what 1,000 turns and a length of what 330 centimeters carries a current of what 5 hot ampere. Calculate A, the magnetomotive force, and B, the magnetizing hot force. This one, you can see that the length is in hot centimeters. So what you have to do first is sort change the centimeters to meters before hot solving. Change the centimeters to meters before solving. And the first one you have to calculate for what? The magnetomotive force. The first one you have to calculate for what? The magnetomotive force. And the second one you have to calculate for what? The magnetizing force. Let's go back to the formula of what? Magnetomotive force. The formula for what? Magnetizing force. Let's see what we have there. But first of all, make sure you write your data down before solving. The formula for magnetomotive force is what? The number of turns times what? The current. So this is the formula you are going to use. This is the formula you are going to use. Now, so you can write this formula down. At the same time, write what the formula for what? The magnetizing force, which is what? The magnetomotive force, which is Ni all over what? The length, which is what? L. I'll call someone to answer. But first of all, change the length to what? Change the length from centimeters to what? Meters. Okay, change it from centimeters to meters. 100 centimeters make what? 1 meter. What's going to be 330 centimeters? You divide by what? 100. You divide it by 100 to get the meter value. Then you use it. So make sure you do that. Make sure you do that. Okay, I'm a mature. I'm a mature. Yeah, please. What's the first answer? Magnetomotive force. What's the answer there?
5,000 ampere turns.
5,000 ampere turn. Let me verify your answer.
Yes, sir.
You can mute yourself. You say you had 5,000. Okay. If you finish, you can raise your hand. Let me call you. Bisa Nana Kofi. Bisa.
Yeah,
Bisa.
yeah.
Yeah.
I also had 5,000 ampere turns.
5,000 ampere turn. Okay, okay.
Oh, you mean the second question?
Yeah, the second question, the A.
Okay.
That's good. Yeah, I'm okay.
Okay.
Yeah, Theophilus.
So I should give the B.
No. Don't give the B.
Okay.
I'll call almost to give us the B. Theophilus. Sebwabe. Sebwabe. Yeah.
Say,
Yeah, what's your answer?
say,
What's your
had
answer?
5,000 ampere.
Yeah, it's correct.
5,000 ampere 10.
Yeah, you can either say ampere or ampere 10 is correct. Okay. The tens is just added because maybe you multiply with what? Tens. Because the unit for tens, we don't, there's no unit for it. We just say what? Tens. There's no unit for it. So you can say ampere or ampere 10. You know what I'm talking. Now the second aspect, which is B. Let me call Benoni. 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 Benoni, unmute yourself and answer question B. Okay. Okay. It's okay. Benoni. Yes, give us the answer. Bisa, mute yourself. Yeah, Benoni, I'm waiting. What's your answer? The B. Yes.
So I think his audio is not working now.
His audio is not working.
That's what I think he said.
Okay.
Yeah.
Okay. Then Bisa, give us the second one. The B. Okay. Okay. Bisa, mute yourself. Let me call some hands are up. Let me call them one by one. Theo, give me your answer. The B.
So I had 1.51 times 10 to the power negative 2 ampere per meter.
Ampere per meter. Okay, thank you. Yes, Kudoda. Kudoda. Yeah.
Sir.
Yeah. What did you get? Tell us your answer.
Sir,
Do you know what you do? You see, the first one, they just multiply the current with the tens. So 5 times or the
Yes,
1,000, that's 5,000. So after getting the 5,000, you divide it by the length.
yes, sir. I have the answer.
And did you change the length to meters? Did you change the length to meters before dividing it? Queen. Okay. Queen.
Yes, sir. Yes, sir.
So what did you have? What's your answer? Tell us.
So 1.51 times 10 exponent -3.
Okay. Mute yourself. Let me call the last person. Frank Nukunu. Frank.
Yes, sir. I got 1.515 times 10 exponent -3 ampere per meter.
Okay, that's good. You are all doing well. Now let's go to the third question. Now this one, we weren't giving her the current, but you all know current can be calculated. Yeah, Nicolas Avognon. What's wrong?
Sir,
Yeah,
sir,
yes.
please, I need the formula for the magnetizing force.
Okay, let me go back and you see it. This is it. The Ni over hot L. Ni over L. And the Ni over there is what? The magnetomotive force. So after finding the magnetomotive force, you just divide it by what? The length. Do you get it?
Yeah.
All right, thank you. So the third question, you can see that current wasn't what given to us, but you can calculate for current if voltage and resistance is given to you. So now a voltage of what 240 volt is applied to a coil having 1,000 turns and has a length to be 3 meters and resistance 25 ohm. Calculate the A, magnetomotive force, and B, the magnetizing force. Yeah, Bisa, I can see your hand up. I miss you. Bisa, tell us the answer. Yeah. Yeah, Bisa.
Okay, the magnetomotive force, I had 9,600 ampere
9,600
turns.
ampere turns.
Uh,
And the other one you had what?
and the B,
Yeah.
I had 3,200.
Okay, you divide it by 3. Since you have 9,000 divided by 3, you get 3,000 something. Okay. Thank you. Mute yourself. Let me call another person.
Sir,
Yes.
sir,
Yes.
sir, they're
Yeah.
supposed to show us how they did it too, because some of us
Yeah.
don't understand.
Don't worry. Don't worry. Omo.
Mm. Yeah.
Okay. Omo, do you know this formula? V equals IR.
Yes.
Yeah.
Okay.
Ohm's law, right? V equals IR.
Yes.
The V was given in the
Yeah.
question, is that also? The R was
Yes.
also given in the question. So make I
Yes.
the subject and find the current.
Okay. Thank you.
Yeah, so do it, let's. Who else got the same answer? Raise your hand. Let me see the number of people who got the same answer. Bisa got. Okay, Tio. Yeah. Okay, Frank Nukunu. Okay, Rejoice. Sedinam. Okay. So 5 out of 15 people. And who else? Let me. Okay, Jasper too. Okay. High ball. Okay. Okay. Awaga. Awaga,
Sir,
yeah. Did you get the same answer?
sir, please, you should come again with the answer I got.
Okay, Bisa, it's up to you. Come with the answer.
Okay, for the A, I had 9,600 ampere turns. And for the B, I had 3,200 ampere per meters.
Okay, thank you.
Yes, sir, my answer is correct.
Your answer is correct.
Yeah, I got it.
Sir, I got it.
Okay, okay.
Yeah.
Let's all clap for Omo. Wow. It seems in the house you are doing better. That's good. Okay. Hey, Nicholas. Nico.
Yo.
Yeah, tell us something. Did you get the answer?
So I got it, but I didn't come here.
Oh, okay. I'm clapping for you. That's good. Okay, now let's continue.
You will so.
So this is how you go by it. The question one is what? You have 15 hot ampere or 15 ampere turn. And this one also I said change the centimeter to meter before solving. I didn't solve it. And this one also find the current by using the formula V equals IR. Then you solve using the same approach. Now let's look at the force on a conductor carrying current placed in a magnetic field. How to calculate the force on a conductor carrying current placed in a magnetic field. This is represented by the formula F equals Bil sine theta. F equals the BIL sine theta. Where the B over there represent the magnetic flux density. The magnetic flux density. Magnetic flux density. Anytime you pass current through a conducting wire, there's going to be a magnetic flux set around it. Okay, so the magnetic flux, or sometimes the B is also called the magnetic field strength. The strength. So the field that is going to be set around it is what we call the magnetic flux or density, and the I over there represent the current passing through the conducting wire, or a current passing through the wire. And the L over there represent the length of the wire. And the theta is the angle of inclination of the wire. Or you can say the angle.
So please, I can't hear.
You can't hear. Okay. I said the formula is BIL sine theta. That's if you want to calculate the force on a conductor carrying current placed in a magnetic field. So if you want to calculate the force, let's say you want to you have a solenoid, you want to calculate the force around that conductor, or the conductor carrying that current. If you want to calculate the force, is given by the BIL sine theta, where the B over there represent the magnetic flux or density, and I over there represent the current passing through the wire, and the L over there represent the length of the wire, and the theta over there represent the angle of inclination of the wire. Theta represent the angle of inclination of the wire, or the angle between the magnetic flux density and the current. So let's look at some factors. The factors affecting the force that has been exerted. Factors affecting the force being exerted. Now let's go back to the formula. You can see that F is directly proportional to the magnetic flux density is directly proportional to the current, is directly proportional to what the length of what the wire, because it's F equals what BIL. If it's like, okay, F equals 1 over B, that one is inversely proportional. But this one, there is no 1 over what the BIL is what F equals what BIL. So they are directly what proportional. That means if what the magnetic flux density increases, the force will what increase. If the current passing through the wire increase, the force will still what increase. If the length of the wire increases, the force what increases. So let's look at the factors affecting this force. The formula, we'll use the formula to what reduce everything. Now, looking at the formula, we said F equals what BIL sine what theta. And we said what the force is directly proportional to what the B, the I, and what the L. The force is directly proportional to the B, the I, and what the L. The I over there represent the current. That's why the A, you see current. When the current increases, the force also what increases. When the current increases, the force what increases. That means when the current decreases, the force will also what decrease. So if you take a solenoid, for example, and you pass, let's say, 3 amperes through what? You pass 3 amperes through what? The coil, and another one you pass what? Let's say 5 amperes through that coil. The one that will have the greatest force is going to be what? The 5 ampere one, not the 3 amperes, because 5, the current 5 is greater than what? That of what? The 3. So the force in what that will be generated in what the 5 ampere one will be greater than the force that will be generated in what the 3 ampere one. Hello, hope you guys are hearing me and you are getting what I'm demonstrating.
Yes.
Yeah, are you getting it?
Yeah.
Okay, thank you. Hey, whose speaker is
No,
that?
no, sir.
Who said no?
Sir, please me. Nicholas.
Nicholas. Nico,
Sir.
Nico, what we are
Sir.
saying is that okay. If you have a conductor and you, let's say you pass current through that conducting wire, let's say you have a wire, then you wound it around this conductor. Let's say this is my conductor, let's say a nail or an iron. Then you wound hot a metallic out, let's say a wire around hot this conductor. And you pass current through it. What's going to happen? You are going to induce magnetism into what? The object being used. That's what, let's say the conductor. You are going to induce current into what? The conductor. That current being induced into the conductor will induce what? Magnetic flux into what? The conducting hot material. Or magnetism is going to be induced into what? The conducting hot material. So there is going to be a flux set around it. Let's just forget about that one. And we said what? Force is what? If you look at the previous formula, Nicholas, look on your screen. If you look at the previous formula, we said the force is represented by what? BIL what? Sine what? Theta. The force is represented by BIL sine theta. Now, let's say you have BIL sine theta, F equals BIL sine theta. That means if they are directly hot proportional. For example, if I say Y equals X, they are hot directly hot proportional. So let's say if S is hot 5, that means Y is also going to be hot 5. They are hot directly hot proportional. But if I say, okay, let's say Y equals hot 1 over hot X, they are hot inversely hot proportional. But you can see that this one, there is no division. It's just straightforward. F equals what? BIL sine theta. F equals BIL sine theta. There is no over. Let's say the formula, you didn't see anything like, okay, F equals 1 over BIL sine theta. It's what? F equals BIL sine theta. So they are directly hot proportional. Since they are directly proportional, if B increases, F will hot automatically hot increase. If I increases, F will hot increase. If L increase, F will hot increase. Nico, did you get our explanation? Nicholas.
Yes.
If B increases,
Sir.
F will increase. If I increases, F will still increase. If L increases, F will increase. Yes, you said?
I get it.
Okay. The I over there in the formula represent the current. So this is the explanation over here. I said when current increases, the force, which is the F I was mentioning, also increases, and vice versa. When it decreases, the F will also decrease. When it increases, this one also increase. Please, Nico, mute yourself. So now, magnetic flux density is the B over there. That one also, the bigger the magnetic flux density, the bigger the force. The bigger the magnetic flux density, the bigger the force. Then the C, the length, which is the L in the formula, the length of the wire. The bigger the length, the bigger the force, and vice versa. And now let's come to the angle. Angle theta. You know, angle theta is also included in the formula. Now, if the angle is 90 degrees, that means we are going to have F equals BIL sine 90, because our angle is 90. Let's go back. The formula is F equals BIL sine theta. Now, our theta there is 90. Let's assume that it's 90. If theta over there is 90, that means it's going to be F equals BIL sine 90. And sine 90 is 1. Sine 90 is 1. If you have a calculator, you can check. Sine 90 is 1. So you have your F to be equal to what? BIL. F will be equal to what? BIL. Whenever you have your theta to be equal to 90, that means your force is at its maximum position. Now that means you've attained your maximum force. So the maximum force occurs over here when theta is 90 degrees. Maximum force occurs when theta is 90 degrees. Let's look at when, let's say, our angle, which is the theta, is 0 degrees. Now, if theta is 0 degrees, what happens? The force will be at its minimum point. Let's say you have your minimum force when theta is 0 degrees. Why are we saying that? If your theta is 0, sine 0 is 0. And 0 times the BIL will give you 0. So your force will be 0. Let's go to the formula again. We said F equals BIL sine theta. Now our theta is 0. Sine 0 is 0. So 0 times L times I times B, all of them is going to give us 0. So the F is going to be 0. So the force will be at its minimum when theta is 0 degrees. When theta is 0 degrees. Now let's look at this question. You can solve it on your own before even looking on the screen. You just look at the question and start solving because the formula was given in the previous slide. Question number 1. A wire of length 25 centimeters. A wire of length 25 centimeters carrying a current. Oh, there was a mistake there. A current. A wire of length 25 centimeters carrying a current of 5 ampere is placed in a magnetic field of flux density 2 Tesla. Note this, magnetic flux density, the unit is what? Tesla. The unit is Tesla, which is what? Capital T. So let me read over the question again. A wire of length 25 centimeters carrying a current of what? 5 amperes is placed in a magnetic flux. Sorry, is placed in what? A magnetic field of flux density 2 what? Tesla. If the wire makes an angle of 30 degrees with the magnetic field lines, if the wire makes an angle of 30 degrees with the magnetic field lines, A, calculate the force exerted on it, and B, under hot condition is the force maximum, and hot is that force, or hot is the force, and hot is that force. There was some typing error. If you've done it on your own, you can raise your hand. Tell me, yeah, so that I'll know that, okay, you are ahead of us. All right. As you can see, the solution is over there. First of all, the data. You see, I've given the data first before solving my hot questions. Now, hey, I'm coming. Okay. Now, the magnetic flux density in our data, B, is what? Equal to 2 hot Tesla. If you read the question very well, I said anytime you see Tesla, it means it's what? Your magnetic flux density. So B is what? 2 Tesla. Now, the current I over there, the current I is what? 2 ampere. 2 amperes. And the length of the wire L is what? 25 centimeters. And the length of the wire L is what? 25 centimeters. You can see that I've changed the centimeters to what? Meters. You can see it on your screen. You just divide by what? 100. So anytime you have a centimeter value given to you, to get the hot, its equivalent in hot meters is what? You divide it by hot 100. You divide it by 100. So 25 divided by 100, you get what? 0.25 meters. And the angle theta over there is what? 30 degrees Celsius. So this one, the formula, you know the formula already. F equals what? BIL sine theta. The data is already there. So if you write your data down, you see that what? Everything becomes simple. You just input your data into what? Your general hot formula. So F over there is what? BIL sine theta. You put everything into it, which is what? 2 times, because our B is what? 2, times I, which is what? The 0.25, times L, which is what? Our 5, times sine what? 30 degrees. And you get your answer to be 1.25 Newton. This one, you just use your calculator. Use your calculator. You not pay for it. Use it. So the final answer for the A aspect is what? 1.25 Newton. And B over there, we have to calculate for what? The question over there is what? Under hot condition. Under hot condition is the force maximum. And hot is that force. We know that our force will always be maximum or reach its maximum position when hot. theta is what? 90 degrees. So it will be maximum if what? Theta is what? 90. I made mention of that. If theta is 90 degrees, your F will be hot at its hot maximum point. So, and they say hot is the force at that point. So if theta is 90, that means sine 90 is what? 1. Sine 90 is 1. So you have your force to be hot, BIL. Your force will be equal to what? BIL. The sine over the sine theta is what? Sine 90 is already hot, 1. So F equals what? BIL. Yeah, Waga, what's wrong? So F equals what? BIL. So now, what's going to be our force now? You just input everything without the sine hot 90. Because sine 90 is hot already hot. Already 1. So F equals what? BIL. So our F is going to be 2 times 5 times 0. Hot 25. 2 times 5 times what? The 0.25. So you get,
Sir,
yeah,
I want to ask a question.
yes.
Is it that if the force is maximum, it must be 90 degrees?
Yes.
Then if it's minimum, it must be 0.
Yeah.
Okay.
Okay. Thank you. So you just multiply your values over there, which is 2 times the 5 times 0.25. You get what? 2.5 Newton. So now, take your pen and be ready to solve the next question. Solve these questions and give me the answers. First of all, write down the data. Make sure you write down your data. I'll give you 10 minutes. After 10 minutes, I'll look at your answers. I'll give you 10 minutes to solve. After that, I'll look at your answers. So solve with maximum rigor. Okay. Now let me hear your answers. Theophilus. Number 1 is Theophilus.
Say.
Yeah. The answers. Just
The
call the
first
answer for
one,
question 1. Yeah.
that's north 34 east. That's the angle, 34 degrees northeast.
Actually, the direction doesn't mean, like, let's say, mention the northeast, or you are just to calculate the angle. So anytime you are asked the direction, just calculate the angle, which is what? Theta. Okay.
Okay.
So tell us how you did it.
Okay, so in the question, per the data, we have the force, that's 0.9 Newton. The magnetic flux density, that's 0.4 Tesla. And we have the length to be 50 centimeters. But if you change it to meters, you get 0.5 meters. And you have the current to be 8 ampere. So if the force, you use the formula F is equal to BIL sine theta. So if you substitute in the values of F, B, L, and I, you get F is equal to, that's F is 0.9 is equal to 1.6 sine theta.
Okay.
So you divide through by 1.6, then you get sine theta is equal to 0.9 over 1.6. So you find the sine inverse or the arc sine of 0.9 over 1.6 and you get 34 degrees.
Okay.
So that's the direction.
Okay. Thank you very much. Amadi. Hey, Nico, mute yourself. Amadi. Amadi.
Yes, sir.
Yeah, what's your answer?
Yes, sir.
One. The first one, what's your answer?
My answer is 34.23. 34 degrees.
34 degrees. Okay, thank you. Mute
Degrees.
yourself. Now, Jason Awaga.
34 degrees.
Yeah, man. Thank you. Okay. Now let's move on to the second question. The second question. I'm a macho. I'm a macho. The second question.
See, I'm not done.
You are not done. Okay. Thank you.
Yes.
No, not Awaga. Amadi. Amadi.
Yes, sir.
The second question, what's your answer? The A.
Yes, sir.
What's your answer? The second question.
The second question, A, I got 0.028 Newton.
Okay, I hear. Let's verify. Yeah, rejoice.
The same thing, 0.28.
Okay. Please, did you change the millimeters to meters? Rejoice.
Yes.
Okay. So when changing the millimeter to meter, how did you do?
1,000 millimeters equal to 1 meters. So the 28 millimeters is 0.028 meters.
Okay. Okay. So if, or you can say, let's say 28 times 10 raised to the power hot. Milli is what?
-3.
-3. So 28 times 10 raised to the power -3 meters. So that's what the length you are going to use. And the current over there is what 4 ampere. And the flux density is what 5 Tesla. So just input.
Sir.
Yeah?
Sir.
Yes.
Please, what's the answer? What's the answer?
I'm just verifying. I didn't solve it. So I'm verifying from you how you did it. Yeah. You? You?
Say.
Yeah. Did you get the same thing?
Say.
Did you get the same thing?
No, I had 0.28 Newton.
0.28 Newton. We are still going to use the same formula. Is that not so?
Yeah.
And your length now will be 28 times 10 raised to the power -3 meters.
-3.
Did you do it?
Times 4.
Times 4.
Yeah.
Times what? The 5. So this
times
this
0.5.
Times 0.5. So sine 30 is 0.5, right?
Yeah.
Yeah. So what you are going to do,
yes.
Those who didn't get it, let's say the formula is what? BIL sine theta. The B in the equation is what? 5. The I in the equation is what? 4. So 5 times what? 4 times L, BIL. 5 times 4 times the L. L is in what? 20. Is the unit is on millimeters. We have to change it to what? Meters. So to change it to meters, 28 times 10 raised to the power -3. So 5 times 4 times 28 times 10 raised to the power -3 sine what? Theta, which is what? Sine 30. And sine 30 is what? 0.5. So if you multiply, then you get your answer. So you say your answer is what?
0.28 Newton.
Okay, thank you. And Amadi, what was your answer?
So my answer is 0.28.
0.28. Yeah, so that's the answer. Jasper. Uma Jasper.
Say.
Please, did you get the same thing?
Say.
The answer?
Yes, please.
Okay, thank you.
0.28 Newton.
0.28. Okay. Kudoda. Kudoda. Amadi, mute yourself. Why? Kudoda. Amadi, you are not the host. Mute yourself. Kudoda. Okay. Maswa.
Sir.
Did you get the same thing?
Sir.
Eh?
Yeah.
Oh, okay. Now
Yes.
let's continue. And the third one. No, the B aspect. Calculate the force. Sorry, the question over there. Calculate the force if the angle made is 50 degrees. If the angle is at 50 degrees. The first person I'll call is okay, Jason. B, how's your answer?
Sir, 0.43 Newton.
0.43 Newton.
Yes, sir.
0.43 Newton. Amadi, did you get the same thing?
Yes, sir.
Okay.
Yes, sir. Yes, sir.
Okay. So that's it. So if you have to calculate for the magnetomotive force, the magnetizing force, and the force on the conductor carrying current in a magnetic field, you know what to do now. Let me hear the house. Hello?
Yes, sir.
But you know how to
Yes,
do it?
sir.
Okay. So
Yes.
the next time when we meet, we'll do talk and I'll continue from there. We'll see what is a talk and look at some the formula for talk and how do some calculations under it. Then we move on from there. Thank you very much for your participation for today. This brings us to the end of today's session. Keep on protecting yourself from this pandemic, this coronavirus. Make sure there is social distancing, use sanitizer, alcohol based one, of course. Yeah. Thank you very much. Bye. Let me hear you all, then I end the class. Yeah.
Okay, you are welcome.
I'm welcome.
Okay, sir.
Okay. Then bye-bye.
Okay, sir.
Bye-bye.
Bye-bye.
Bye. Bye.